Hello guys, this is Abhijit, and today in this lecture series we'll discuss what is wave function part 2. So we already discussed in our part 1 about the most important equation that we called as equation number 2. So what was equation number 2? Equation number 2 is nothing but it is made up of the classical equation E equals to P square divided by 2m. Okay, so when we go from the classical to the quantum mechanical, what we do, we replace the E with h cross omega and we replace the P with h cross k. I hope you remember this. Okay, and we get the equation now. And then we also studied that this equation 2 is very important, and this equation 2 can also be derived from equation number 3. Okay, you can see equation number 3 here. The equation number 3 is the so-called Schrodinger equation. Okay, so what does equation number 3 does? It says let the electron is represented by wave function psi, and that wave function psi, when you put in equation number 3, you get the equation number 2. Okay, so what does the wave function psi is? The wave function psi was complex, we saw in our last lecture. And what is the meaning of wave function psi? We had no idea. We just did some mathematical trick. What we did in the last lecture, we assumed a particular psi that represents the electron. Okay, and we put, and the psi contained the information of energy and momentum, and then we cleverly made some differential equation that will snatch out the the information of energy outside and the information of momentum outside, and that would make equation number 2. This is what we did. So if you forgot, then please go to the lecture again and please watch it. Okay, what is wave function part 1? I'm not going to discuss it any further. So this is what we did in the last lecture. Now moving further, is our plan was to understand what is wave function. Okay, we know that the wave function was complex and we had no idea, not a single bit of idea, what the wave function actually represents. We just assumed the wave function represents an electron, but then the wave function turns out to be complex. Now, how the hell a complex thing can represent an electron? Now, that's a problem. Okay, so what to do to understand the wave function? Just forget it. Forget what you have learned from me till now, and please watch this lecture from now on with a fresh mind. Okay, so what we are going to do, we are going to look at the experiments again with a bit of mathematical touch that led to quantum mechanics. So this particular experiment here is the experiment for diffraction pattern of light. Okay, so what happens here? So when you pass the light through a particular slit, you get a diffraction pattern here. So what is the diffraction pattern here? The diffraction pattern here says that you have maximum intensity here in the middle. Maximum intensity means the light is more there. You see a strong intense light on the screen at the center, and as you go up or as you go down, the intensity of light decreases, and there are points where the intensity of light is zero. I mean, there are dark points. So this is a dark point, this is another, this is another, this is another. These are all dark points where the light is zero. I mean, there is no light, or you can say light plus light is no light. Agreed? So this is a wave nature stuff, and since light is a wave, so it shows this type of diffraction pattern. Now electron behave as a wave and it shows diffraction pattern. Now you would say, okay, let's try to understand this. If this were a machine gun, okay, the machine gun will fire bullets. Since bullets are particles, so they will just pass through the hole of the slit and they will hit at the center of the screen. This is how bullets behave. They don't go up, they won't go down, because they just go straight, because entire momentum is towards the straight direction. Okay, but since our electrons, they are wave, what they do is they not only go straight, they go a bit up, they also go this side. Now who pushes them up and who pushes them down? Nobody knows. That's the truth. We don't know who pushes them up or who pushes them down. This is the uncertainty principle. There is an uncertainty in the momentum in the up and down. Okay, so they behave as wave, and some electron they go up, some electron they go down, maximum electron they go straight, and they form a diffraction pattern. You see this diffraction pattern, what does it says? It says that the maximum electrons, you can find the maximum number of electrons at the center of the screen. Here you find the maximum number of electrons, and as you go up this side or down this side, the electron intensity decreases. I mean, if you move the detector, okay, if you move this detector up or down, what happens is you find the number of electron that is being detected by the detector is less. Okay, so what is detector? You see, you cannot see electron hitting the skin. So what you do is you employ a detector that detects the electron. Say if the detector absorbs one electron, or a electron hits the detector, it gives a sound beep. Okay, so at which place you are going to hear the maximum beep sound? At the center. So that says that the probability of finding electrons is more at the center. Now as you go up, the probability decreases, and as you go down, the probability of finding electron decreases. It means if you move the detector up or you move the detector down, then you'll find that the number of beep sounds are less. It means the probability of electrons reaching the upper side or the lower side of the screen is less. However, to our surprise, there are some dark points. By the dark points, I mean the places where the electron never reach. Okay, so this is one such place, this is another, another. So these are the places where the electron never go. Now how they know that they shouldn't go there? Nobody knows. They just don't go there. There are some dark places which we said that the minima, places of minima on the diffraction pattern, where you never find the electron. If you put the detector there, you will not hear a single beep. So there are no electrons there. Now I would say that how does the electron know not to go there? Nobody knows. That's the truth, but we don't know. Okay, so what do you have? So the detector gives you a probability distribution. Agreed? So the detector says that look, this is a probability distribution, and the probability of finding the electron is more at the center, and it goes on decreasing as you go to the sides. Agreed? So what do we have here? All we have here is a probability distribution P of X. Okay, now what I'll do is I'll modify this experiment a little bit more. Okay, so what I'll do is let me take another experiment. So in this experiment, what I'll do is I'll choke one of the slit and allow the electrons to pass. So what would happen if I close slit number 2? You see, if I close slit number 2, then electrons only pass through slit number 1, and they form a diffraction pattern that is shown by P1 of X. So who gives us the P1 of X? The detector. The detector says that the electron coming out from the slit 1, they are distributed on the space or on the screen that is given by a mathematical function P1 of X. Now what I do is I choke the slit 1. I just close the slit 1 and allow the electron go through slit 2. What the electron does, they go to the screen like this, and they form a diffraction pattern here, and the detector says that hey look, I can give you a probability distribution, and the detector says that the probability distribution here, the center is more, and if you go up and down, it goes on decreasing. So P2X is the probability distribution of electrons coming out from slit 2. Okay, so the idea is, if I open both the slits, what would happen? It's obvious, it's very obvious, both the probabilities should add, and I should get a diagram like this. Okay, I should get a diagram like this. It's very easy. Okay, should get a diagram like this, both the probabilities should add, and if I open both the slits, I should get this diagram. Okay, So the what does this diagram says? That the electron is more here, electron is more here. I mean the probability of finding the electrons are greater here. If you put the detectors here, you hear maximum beep, and as you go up or down, the intensity or the number of beep that decreases, and at the middle you see here you get another minima point where the beep of the detector is less. I mean less number of electron reach that point. But this does not happen. To our great surprise, this just does not happen. The probabilities don't add. While they should add, intuitively they should add, but truthfully and experimentally they don't add. That's the weird thing. So what happened? We get interference pattern. Now this was very difficult to understand. Okay, we get interference pattern like this. What does this mean? If you place a detector, okay, so you get the maximum number of beep at the center, but as you go up and as you go down, there are many points of maxima and minima. By maxima I mean there are points where you will hear beep, and by minima I mean there are points where you will hear no beep. I hope you remember the interference pattern. Now the huge problem is our mathematics is not, it's not gonna work. The mathematics of adding probability distribution, it's not gonna work. We need to find a new mathematics that will help us build our interference pattern. For example, we need a mathematics that would say, hey, of course, if you just open the two slits, you'll get interference pattern, and if you open slit one by one, you'll get diffraction pattern. We need a mathematics like that. Okay, our probability mathematics is not helping. Yes, our probabilities mathematics is helping a bit. It says, okay, if you open slit number 1, you get a probability distribution 1. If you open slit number 2, you get a probability distribution 2. Okay, mathematics is working well here, but the problem is when you open both the slits, then the probabilities don't add. So the mathematics of probability is not helping us anyway to understand quantum mechanics. So we have to reject this mathematics. Now the plan is to find new mathematics that is going to explain this weird behavior of electrons. Okay, we need a new mathematics. So now the problem is, what is the new mathematics? To our help comes the interference that you studied in +2. So in your +2 you studied the interference of light. Agreed? So in the interference of light you might have seen the interference pattern, and who describes the interference pattern well? It is actually the formula of intensity distribution. So this is the intensity distribution that you studied in your +2 physics, okay, in the interference chapter, that well explains the light's behavior and the pattern that the light forms on the screen. Agreed? So now there is a idea. How about linking the intensity that you get in light's interference pattern and the probability that you get in the electron interference pattern? Okay, so the idea is to link them or to think them as one. So in the light, okay, so in the interference of light we have intensity, and there is a formula for intensity that describes the interference pattern. But how did we get the formula for intensity? We used the wave equation of lights coming from slit 1 and slit 2. Okay, remember how we find the interference pattern equation? We just add the wave equations. I mean we add the amplitudes of wave equations. So if you compare the probability in quantum mechanics or the electron diffraction experiment with the intensity in the light's diffraction experiment, then you need something in the electron diffraction experiment that would correspond to the wave equation in the light diffraction experiment. Agreed? So that's our aim. So our aim is, we need something here. You see this line in bold dark with a question mark. We need something that is a question mark in electron, which is comparable to wave equation in the interference of light, because this wave equation was the key to the intensity distribution. So we need something in the electron diffraction experiment that will serve as a key to the probability distribution. Agreed? And that key was wave function, and that key was our wave function. So wave function is something that describes the electron, and using that something we can find the probability distribution. Agreed? And unfortunately this wave function is complex and you cannot imagine this wave function. It is very beautiful in case of diffraction of light. You take the wave equation of light, which is very intuitive. You can draw it on your paper, you can add them, you can subtract them, and you can find the intensity distribution. But in case of electron, we have this wave function that corresponds to the wave equation, but this wave function is complex. You cannot draw it on your paper, but strictly mathematically it helps us understand quantum mechanics. So whenever you are given a wave function, don't try to understand what the wave function is, just try to understand the square of the wave function. The square of the wave function is probability. Okay, so I hope you understood wave function. Okay, so now this particular diagram shows how wave function explains the interference pattern very well. So this is up to you, try to understand it yourself. Okay, if you have doubt regarding this diagram, then please contact us here on the particular Facebook page. You can ask us question on through messages, and so this is a homework for you. Try to understand this, how the size that describe the intensity pattern or the probability distribution of the electron very well. So what is psi? So whenever you are given a psi, okay, so whenever you are given a psi, please think of the psi as a distribution in space. So psi has nothing to do with the electron. Psi has actually something to do with the result of the experiment. I repeat again, psi has something to do with the result of the experiment. For example, if I give you a wave function psi in this blue box and green tick, okay, what if I give you a wave function psi like this and I say this represents a particle, then what you should keep in your mind? You should keep in your mind that this particle is going to have a probability distribution that depends on x, and it is square of this psi. It means if you conduct experiment on this particle, which is represented by this wave function, the experiment is gonna show, the wave function is gonna show the result of the experiment. Okay, so what is the result of the experiment? The result of the experiment is you find the if you have a particle represented by this wave function, then the probability is gonna look like this. By the probability, the result of the experiment is going to look like this particular curve. What does it mean? If you try to measure the particle, you find the particle is maximum at the middle position, and the presence of the particle as you go to the sides is less. So that's a thing. Okay, so that's a thing. This is actually true in case of particle in a box that we will describe in our next lecture. So whenever you see a wave function, keep in your mind the wave function is actually representing the result of the experiment conducted on a particle. If a particle is represented by a wave function, then keep in your mind that that wave function represents the distribution of the probability of the particle. The probability of the particle says where the particle you will find more and where in which places the probability of finding the particle is less. Agreed? So this is a very weird example, but it is true. You know what? If you keep a particle in a box, this is a wave function for particle in a box. So if you have a wall here and if you keep another wall here and you take one small particle that is represented by a circle here, okay, and you keep it inside these two walls and you allow it to bounce. So the weird thing is, if it were a classical particle, then the probability of finding the particle anywhere in between the two walls were same. Is gonna be same. Intuitively you will find you must have the equal probability of finding the particle anywhere between the two walls. But quantum mechanically, the probability of finding the particle is maximum here and the probability of finding the particle is minimum here and here. Why does this happens? We don't know, but it is true. So we'll discuss more on this type of weird wave functions, okay, as we study the application of Schrodinger equation in your particle in a box or one-dimensional potential and everything. So I hope you gained some kind of insights onto what a wave function actually represents. So the wave function actually represents the probability distribution that you get after the experiment. So it does not represent any incoming electron like the wave represents an incoming electron. I mean the wave equation, they represent an incoming light, they can represent an incoming wave source, but the wave function in quantum mechanics does not represent anything incoming. It just represents the outcome of the measurement, or it just represents the probability of the outcomes after the measurement. Okay, I hope you understood wave function. If not, you go through this lecture again. You will get my PDF attached with this lecture, or you can go to my Facebook page to find the PDF and you can look at the PDF to try to understand. Okay guys, thank you. So we'll meet again next week with next lecture and we'll continue our discussion on quantum mechanics. Bye for now.